Alright, so this time around we're talking about sets. This is going to be the underlying math and logic behind collections. So let's quickly get into this. We're going to look at exactly what a set is, how we represent them, manipulate them, read them, all that good stuff. We're going to talk about set operations. We're going to talk about some commonly used sets. These are ones that are given their own specific names. And then lastly, we're going to take a look at some properties of sets, which these should be very familiar to you. If you remember your algebra, you remember your properties of linear equations. So we're just going to dive straight in. None of this should be too terribly difficult. I understand the last math lectures were a bit messy, but this should go by a lot smoother. So, starting off with what exactly a set is. A set, in mathematical terms and in logical terms, is any collection of objects. They need not be numerical, they need not be in order, they need not be containing only unique values. And wow, doesn't this sound familiar? It sounds a lot like talking about lists in Python. So, again, there's no rules to how these collections are organized or what they contain, as long as it is a collection of some sort. And when we talk about sets, each item contained within a set is an element. So if we're given a set called X that contains the numbers 1 through 10, the number 7 is but one element of that set. A fun bit of trivia here is that the concept of sets in terms of mathematics predates that of numbers. So this is a much older concept than any math that you've ever dealt with. And lastly, on this slide, the mathematical concept behind arrays, databases, and other complex objects and things like that. This is the math and logic behind those. You're going to learn more about databases when you get to your higher level classes. Array is just another word for a list. So, yeah, this is, like I said before, this is much closer to programming than just talking about binary and how to add and subtract it. So, how do we write and represent a set? So, the first thing to note is that each set is given a name. Usually, because we're talking in terms of mathematics, it's given a single digit name, or single character name rather, like A, B, C, D, E. Of course, in programming, we would want to give it a more descriptive name. But in our cases, we're talking about math, and math likes its single character variables. So, the next thing to notice is that the contents of a set are wrapped in curly braces. So, to write a set containing the letters 1 through 5, you would write the name, in our case A, equals, and then your contents 1, 2, 3, 5, 4, and a pair of curly braces separated by commas. And I made that first one out of order just to hammer home the point that order is not important. So, let's look at some other examples. If you have an established pattern, like say all even numbers, you can do something like B equals 2, 4, 6, 8, 10, then an ellipse, and then your last number. You can do that. If your number pattern goes off towards infinity, then if the number pattern goes off towards infinity, then your ellipse is going to be the last character set in the list. It's going to be the last item. Another way we can write them is by specifying a given rule or set of rules. So, if we take C here as our example, we see that it is the variable X, and this colon means such that. So if we read this as it's meant to be read, it says C equals X such that X is even. So, therefore, C is the set of all even numbers. So, we can also define compound conditions for our sets. If we look at D here, D equals X such that X is odd, and X is an element of A. That's what that weird curvy E character looks, that it's supposed to read as. So again, that's D equals X such that X is odd and X is an element of A. So, in our case, D would contain the numbers 1, 3, and 5. If we look at E here, this is how we combine two existing sets. This is but one option called a union. What a union does is it takes everything in each set and combines them into one big set. So, in our case, E equals the union of A and B, A being 1 through 5, B being all even numbers from 2 to 50. So, what we have here for E is the set 1 through 5, and then even numbers 6 to 50. And lastly, we have a way to check the contents of a set in relation to another. So in this case, we have F is a subset of B. And this is a true-false statement. So we have, if we were to say F equals 2, 4, 6, 8, 10, then this statement would return true. If we were to say F equals A, and then check if F is a subset of B, well, 1, 3, and 5 are not found in B. So, in that case, if F were to be equal to A, then F is not a subset of B, because A is not a subset of B. And all we mean by subset is the smaller set, in our case F, contains only values that are found in the larger set, in our case B. And we're going to go over more examples in later lectures. This is just part 1. This is just our overview. We're going to do a lot of examples to make sure that this is understood. Some common operations to look at. Again, we have the curved E looking thing, and that is element of. The colon or a vertical bar means such that. And of course we have the subset of, we have union, and then we have intersection. And what an intersection does is if we're given two sets, then the intersection of those sets are the elements contained in both of them. So if we go back up, we have sets A and B. The intersection of A and B would be 2, 4, because those are the only numbers contained in both A and B. Moving back here, if you see a grave accent, or if you see a tilde mark, that is the complement, and that is given a set A, A's complement is everything that is not in A. This one can get a little bit muddy. You can end up with some massive, overcomplicated sets very easily. So I'm going to try to keep those examples simple and also keep them to a minimum. And now if we look over here, we have some common sets. This is not the exact syntax for how these are written. Usually the letters are a bit more bubbled out. It's more like a thick outline containing the characters, but it's okay for our purposes if we just use these letters. So we have N, which is naturals, and this is any non-negative integer. So positive numbers and 0, and only whole numbers. Then we have Z, that is your integers, and that includes all your naturals plus any negative whole numbers. Q, this is your rational numbers. This is, we understand rational numbers that can include integers. It can also include any number with a fractional part that terminates, or that follows a pattern. R, that's your real numbers. This is anything that is a number, that is not a complex number. So integers, that can be positive, negative, or zero. It includes rational numbers, and it also includes irrational numbers, that being numbers with fractional parts that are non-terminating and non-repeating. Now we have the no symbol that refers to the null set, and the null set contains nothing. It is nothing. So, easy to remember, and the exact opposite of that, actually the null set's complement is U, or the universal set. The universal and null sets are each other's complements. Naturally, the universal set is everything. So, looking back at set operations, let's say we have two sets, A equaling 2, 4, 6, 8, and 10, and B equaling X, such that X is a natural number. So, we look at our set operations. Is A a subset of B? Well, A contains only natural numbers, 2, 4, 6, 8, 10. Those are all naturals, so yes. Looking at the union of A and B, that being all positive numbers, and quick correction, natural numbers does not include 0. I apologize. But yeah, the union of A and B in this case is just B. The intersection of A and B is 2, 4, 6, 8, 10, which is just A. B's complement is all non-natural numbers, which is all negatives, all negative real numbers. Bleh. I wrote that incorrectly. It should be all negatives, all non-whole numbers, all non-integers, and 0. That one is a good example of how this can get a little bit confusing. So to reiterate, the complement of B, which is the set of all natural numbers, is the set of all non-integers, all negative integers, and 0. Now if we look here, the intersection of A and the null set contains nothing, so that's nothing. The intersection of A and the universal set is everything contained in A. You could think of this in the same way as anything times 0 is 0, anything times 1 is itself. It sort of operates on that same principle. And for subset of an element of, you're not going to see this anywhere in our assignments, but you can take those and you can put a line through them to negate it. So a diagonal slash mark through the subset of and element of symbols would read as not a subset of and not an element of. Again, here's our commonly used sets and how they are represented. We've already gone over these, so I'm just going to move on. We're going to talk about the properties of sets. You're going to have to explain these in your assignment, so I'm just going to briefly look over them. So we have the commutative property, which applies to addition and multiplication in regular mathematics and also applies to set operations, particularly the union and intersection. The union of A and B is the same as the union of B and A. The intersection of A and B is the same as the intersection of B and A. They are the same. You flip them around, it's all good. If you're given 3 sets, we have the associative property, which states that no matter how we move our parentheses around, when we're dealing with the same set operations, it's not going to affect what that result is. So the union of A and B and C is the same as saying the union of A and the union of B and C. Same thing with intersections. The distributive property. Now, this is something you should all be very familiar with your high school math classes. This is used everywhere when we're talking about multiplying a number by a tuple of some kind. So if we have the union of A and the intersection of B and C, that equals the union of A and B, or the intersection of the unions of A and B and A and C. And the same thing if we flip it the other way around. So if you look at it this way, if you have three sets being joined by the same symbol, union or intersection, the associative property applies. If the symbols are different, then the distributive property applies. Now we have the identity property, and that is basically what we said before. So the union of A and null is A, the intersection of A and U is A. Complement, the union of A and A's complement is the universal set. The intersection of A and A's complement is the null set, because a set and its complement are mutually exclusive. They contain all different elements. And then lastly, we have the idempotent property, which is very simple. The union of A and A is A. The intersection of A and A is A. So that's going to do it for our overview. Next time, we're going to go through a bunch of examples and try to make sure we all understand this loud and clear. It's not going to be terribly convoluted. I'm going to keep the examples nice and simple, so stay tuned for that.